tasked with designing a filament winding machine that is computer controlled, and in this video I'm going to discuss the scope, basically how far we intend to go in this design endeavor. Now, there is an existing filament winding machine, and I'll explain what it is. Of course, I'm sure some of you already know what a filament winding machine is, but I'm going to go into the detail of describing its function a little later. But the important thing is to understand why we even need to do this at all. So this project was actually born out of an existing manually operated filament winding machine. It was created for the production of pressure vessels, 1854 pressure vessels. There were some difficulties encountered in the production because it required more than one person to operate it, and that was not a good, from an economic standpoint, it wasn't a good idea. So in this video, I'm going to outline the scope of our new machine. It's going to be completely computer controlled, and basically it will be based on the previous machine that was built, except that now the controls are completely handed over to computer software. So you basically program its operation and then watch it operate, watch it run. If you need to make changes, you can adjust the program. And then the advantage, of course, in this is that it will be an automatic production machine. So as soon as you fitted a mandrel and set all the parameters, put the required filaments, poured in resin into a resin bath, you will be able to have this operate on its own at the end of a given time period, give you a completely wound filament winding machine. So the scope the scope of our project is to, let me very clearly state it, design and build a computer controlled filament winding machine. Now, the way we intend to do this is to hand over control of all of the axes of motion to computer software, which means you can write a program and control each of the axes independently, and they can operate at this, all of them operating simultaneously to achieve specific design requirements: number of layers, helix angle, number of hoop winds, and all of those parameters. So let me outline the axes. So imagine on a horizontally mounted mandrel, cylindrical mandrel with domed caps, domes capping the both ends of the cylinder. So we will call this axis our mandrel axis. Eventually we'll replace these names with letters that allow us to abbreviate. So this is the mandrel, basically a rotating cylinder mounted on a machine. So there's a frame, obviously. Then there is another axis of movement. There's something called a carriage, and that carriage carries the resin bath, it carries the payout eye device and assembly, it carries the rollers that direct the movement of the filaments. So let us draw a box here and let this represent our carriage. this carriage, we intend to have it move along left and right, just parallel to the mandrel axis. So we'll call this axis of movement our carriage axis. Carriage axis. Okay, so that's the new degree of motion. Then mounted on this carriage, amongst other things, is what is known as a payout device. Basically, it is the point that directly winds the filament over the mandrel. And by the way, I'm sure some people may not be familiar with the term mandrel. Well, if you are new to the world of composites, that's understandable. I'll explain what a mandrel is. Okay, very quickly, a mandrel is simply a shape, a pre-molded shape that is brought into this production process. So with this filament winding process, which is basically the use of a continuous filament of a reinforcing material, which is mixed with a polymer that has been activated. So there's a polymerization reaction already going on within the polymer, so that after the winding process, when the product is kept for some time or cured in an autoclave, that polymerization process will be completed over time and will harden and form a very strong structure. So a mandrel is usually pre-molded. So if you want to make a cylindrical filament wound vessel, you need to make pre-mold a mandrel in the shape and size, all the dimensions. The mandrel allows you to, control those parameters very tightly. So we have a mandrel here rotating along its central axis. I was talking about the payout axis. So basically, this payout axis that directly winds the filament over the mandrel, it needs a degree of freedom. Okay, it needs to be able to tilt. So we'll call that our payout I tilt axis. Payout I tilt axis. Okay, and of course it moves with the carriage. So we have our carriage axis, we have the payout I tilt axis, we have our mandrel axis. So with these three axes, this is a 3-axis filament winding machine. You want to stop here, although there's an enhancement that you can obtain from having this payout I device also have the capability to not only tilt but also rotate. Okay, so we will decide whether we want to go that far, but with a 3-axis machine, there's a whole lot you can do already. If it's an enhancement that we want to add later on, I think that it's very well within our capabilities to do that. So we have this is the basic layout. Okay, this is the basic diagram of, well, I guess a functional summary. I have not drawn the frame upon which all of this is mounted, obviously. So basically, the machine will have a frame that holds all of these components we've just described. It's also going to have a mandrel axis and the mandrel axis drive components. Okay. And on the mandrel axis, the important components are the mandrel holder. Okay, so basically you need to be able to pick mandrels, because imagine in a production scenario you're going to have a number of an inventory of pre-molded mandrels stacked up ready for filament winding. So you need to be able to install them on the machine, and then after the winding process has been completed, you also want to be able to get that mandrel out of the machine and then load a new mandrel to repeat the process. So it's going to have a, on the for the mandrel axis components, you need to have a mandrel holder, then you need to have the drive components, okay? Essentially, the mechanism that is going to cause that mandrel to rotate as needed. And then we'll talk about the carriage axis. So the carriage axis basically is constrained to translate back and forth along the mandrel axis, okay? That is parallel to the mandrel axis. So to make it do that, we need to have a carriage axis guide rail. This is the carriage axis components. So you need to have a guide rail assembly. The guide rail assembly allows the mandrel to smoothly slide along the carriage axis, okay? And then we're going to use lead screws. There are many ways, basically in order to move, we have with the guide rail assembly, you have a carriage that is capable of sliding back and forth along the carriage axis. But how do you make it move? You need a lead screw, a way to apply force on the carriage to make it move back or forward, okay, to make it go forward or backwards. So you need, we're going to use a lead screw to do that. There are other ways that we can do that. We can use a chain and sprocket system. We can use a timing pulley system. There are lots of options that we have in that regard, but specifically we will go with a lead screw driven by a stepper motor. So we have a lead screw assembly. Basically a long screw that has got, it's mounted between bearings. On the other end, a section of that screw sticks out and allows you to attach a shaft coupling to a stepper motor that connects them together so that the stepper motor can rotate and achieve specific distances. And let me quickly describe, I've mentioned the stepper motor now, but I think an introduction of what it is helpful, I think. So a stepper motor is a special kind of motor that allows you to have positional control. Okay, unlike regular motors like a DC motor or an induction, synchronous motor, whatever, a stepper motor allows you to move specific distances, allows you to use computer code to move, make very controlled movements. So we can do that by, when we have the transmission ratio, that if it's a direct drive, then we can calculate the distance moved when one step of the stepper motor. Basically, the movements of the stepper motor are called steps. Okay, so usually there are many steps depending on the specific design. But for the purposes of our work, we will write code, computer code, that will cause the stepper motor to make one step, and then we need to know, we'll calculate what that step translates to in terms of linear distance, and that will allow us to achieve our aim so that our software can very precisely control the movements. So you have a lead screw assembly, which is driven by a stepper motor. That is that will drive the carriage axis. Then the payout eye tilt axis payout eye tilt axis. Basically, what the payout eye is it's, as I mentioned before, it's the final point that winds the continuous filament. And by the way, the filament comes in rolls, okay, large rolls, and usually you're going to have all of that mounted on a frame somewhere next to the machine, and then that machine will pull as the mandrel rotates. It will continuously pull that filament through the payout eye device, and that payout eye for the cylindrical length of the mandrel. Yes, I was speaking of the payout eye. So for the cylindrical length of the mandrel, it doesn't need to tilt. The payout eye device does not need to move when this filament winding machine is winding over the cylindrical segment. But when it gets to these domed caps, because of the curvature around here, it needs to tilt in order to properly wind the fibers over the mandrel. So that's why it needs that additional degree of freedom, and we achieve that additional degree of freedom by creating a mechanism that allows that payout eye device to move, to tilt, and then we control that using a stepper motor, and then use instructions from our program, our computer program, to decide how much it moves and when it moves. And then of course when it gets to the straight cylindrical area, it will orient itself back to its default position. So that is how this payout eye tilt axis is intended to operate. We can of course add an additional degree of freedom by making the payout eye device not only tilt when needed, but also rotate. Okay? That additional freedom would allow it to behave even more, kind of orient itself more perfectly. But for a 3-axis machine, there are lots of things you can do already with the 3-axis capability, so it's not necessary to go that far. But we may decide to add that enhancement down the line and put an additional axis. But of course, the more axes you're dealing with, the more complicated your programming will have to be in order to make it all work well. There are control software for filament winding machines, but they are very expensive software. There's no open source solution for filament winding as far as I understand it. But we will write our own program to run our specific task of winding over this 1354 filament wound pressure vessel. And that is as far as it goes. With the steppers, they will be sized appropriately depending on the task. So for example, the mandrel axis is um, the axis that actually determines the tension that generates that force to pull the filaments. So that obviously will have a different torque requirement from the requirement um, to move the carriage axis to and fro, and that also will have a different requirement from what is needed to tilt the payout eye. But the common thing they all share is that these are very precisely controlled motors, and you can even improve the output you get from them by using a transmission, building a transmission. And so using the transmission ratio to enhance the resolution of the motion resolution, so that if you want very high resolution movements, you can use a transmission to enhance and get that. And we'll go into those details. We'll go into actually every detail. We'll have the circuit diagrams. We'll discuss all of the details, how everything operates. That is the objective, and we will go through all of it. So the stepper motor needs to be connected to a driver, what is known as a driver, basically a device designed to operate it. It's not just like a DC motor. You just have two positive and negative terminals, and you apply a voltage and it starts to rotate. This one has many windings within the motor, and a computer can activate a series of windings in a particular sequence to achieve different kinds of motion required.